With us, today's speaker is Dr. Vivek Kumar Singh. The title for today's talk is Advancing AI for Cyber Defense in Power Grids Detection, Explanation, and Resilience. Dr. Kumar is a senior researcher for Cybersecurity Research Center within NREL. He leads technology commercialization projects, including collaborations with industry vendors and initiatives focused on developing cybersecurity tools and technologies to secure DERs. Vivek is working on developing secure AI algorithms with privacy-preserving methods to develop anomaly detection and mitigation approaches for the power grid. He worked at INL in the Power and Energy Systems Group in the year 2020-2021. He also involved in a number of proposal writing and development with internal partners from other national labs. His research interests include CPS security for smart grid, wide area monitoring, protection and control, hybrid energy storage systems, AI security, and cyber physical federation testbeds. He has received awards from U.S. Army Research Laboratory, North American Synchrophase Initiative, and Iowa State University. He has published several research papers, patents, software disclosed records, and featured in several media articles. He also received awards at Resilience Week 2018 and 2020 and 2020 Texas Power and Energy Conference. Dr. Kumar, Vivek Kumar, thank you for joining us for this webinar series. It's an extreme honor to have you again. You've been very significantly contributing to the center's growth. I appreciate for coming and supporting us, and the floor is yours.
Thank you, Dr. Prakash. This is great. Thank you for your nice introduction. I just want to say that Doctor has been doing really great job. He has been making sure that UND, your university, has been heard to be one of the pioneer in cybersecurity for grid as well as other IoT devices. So thanks for all your effort that you have been doing so far. And as an NREL employee, I can tell you we are always willing to collaborate with you, and we had very good past experience in writing and working together. So I'm hoping to continue the same kind of conversation as well as engagement in future. And with that, let me share my screen and can you guys see my screen?
It's coming. Oh, hold on, maybe.
Okay, let me see. Okay, yeah, it should be good now. Uh,
Started sharing. Okay, yeah, we can see now. Yes.
okay, awesome. Yeah, let me see if I can pull the pointer out. It's helpful when I'm talking about specific thing. Okay, cool. Thanks everyone for joining this seminar. This is Vivek. Like uh, Professor was saying, I'm a senior researcher at NREL, and today I'm going to talk about the different types of AI work that NREL has been doing so far. And I feel like most of the national lab is going in the same direction. Our focus is to completely try to understand how AI is going to help you, or what are the security challenges you might see with the AI, and what are the threats that might also come from the AI. So we're trying to explore different dimensions of AI at NREL, and I will talk about some work that at NREL we have been doing, and also our future plan for the next 2 or 3 years. In this presentation, I will be talking about the AI and cybersecurity, like more like a challenges and opportunity at the same time. Also, for the past 4 years, I've been working on the tool called CySAT, and we have done a lot of case studies. It started from the hydropower office, then Caesar got the recognition of this tool. They funded more money to continue working on this kind of tool, and we are trying to also make this tool to be deployed by some industry vendors. So we had really good outreach with this tool, and we are trying to do more case studies from the CySAT tool that we had at NREL. At the same time, our group is also exploring other area of AI domains, like one of them is called explainable AI, and I'll talk more in details. And then there has been some effort in going into the deep reinforcement learning to develop anomaly mitigation system. And finally, I would be talking about some future work where NREL is moving forward. And also, I'm happy to have some kind of ongoing discussion that we can think about how we can work together in this domain. One of the slide that we always mention when we start the presentation at NREL is we give like a high level picture of the whole power grid, which is very common and a lot of people are very much familiar. And the idea is to make sure that how do we see this problem at the global scale at a high level where we see there's a lot more bulk power generation are happening. Like hydro is always there. We have seen hydro plants. So we at NREL we are trying to deploy more hydrogen plants at the ARI site, and we have a lot more contracts going on. Then we are also looking into geothermal because that's where the funding is gonna be more. Energy storage was always there. It's always gonna be a part of big energy resources that could be for the hydro or hydrogen, even for the PV also. And wind farm is like not much interest to the DOE at this point. Mostly, even you go and talk to some industry like GE, they're trying to move their market towards Europe for the wind farm. So, whenever all these changes happen, you have to be more prepared and what kind of work you need to do so that you keep receiving more R&D funding and you continue working in this domain. And then on the other side, we have seen a lot more EVs getting connected to the household. But with the new administration, this may not be our main interest. But at the same time, we are looking into virtual power plants. We are seeing how your multiple smart meters and you have all these AMI sensors that is connected on the customer side. The data is very useful. And when you talk about the AI, you need to have lots of data from the customer side as well as from your bulk power generation. And we also have seen a lot more interconnection happening at the transmission and distribution side to make sure the power could be transferred back to the customer side. Customer is not just consuming power, they're also supplying power by connecting more EVs to the ancillary services or putting more rooftop solar so that they can generate more power. Because in general, the pricing would be going to increase because if you think about more data centers coming, the utility is going to give more preference to those data center because that's where the profit is. So at some point, it won't be, it's very obvious that we might see a lot more rooftop solar being deployed by each customer into their household. And then we are also seeing a lot more 5G communication happening. There's a cloud access happening to either data centers as well as to the grid in general. And then also there's a like a cloud level security has to be also looked into. And that's where we also exploring at NREL too. So there's a lot more things to talk about, and like I'm gonna just leave it over there. But like I said, there's a lot more problems gonna get complicated. But in general, what we are trying to look into the data challenges where we see a lot more data getting deployed at the device level. We also see that the data doesn't come at the same sampling rate. There are so much diversity in terms of data set because of multiple devices, the systems, and the way that it works, as well as the users. There's a lot more diversity of data sets. So we are trying to deal with heterogeneous kind of data sets. And then we also seeing a lot more communication standards, protocols getting deployed at the grid that make the interaction very complicated. And they, again, I guess I'll tell the same thing. They have very different sampling rate. They rely on different types of interfaces. Their communication protocols are very different. So finding the interoperable interface is the big challenge in the grid. And the last one is like the how do you make a timely decision? Like when you collect the data, you know what happened. How do you try to uh, do something, try to take an action that would be useful for the grid? That's something which also require a lot more detailed investigation as well as make sure that your actions are not being triggered by the false alarm. It has to be trustworthy and has to be accurate. And so there are multiple challenges happening, and our goal is to see what we can do to understand these challenges and try to find some possible solutions into that. So in this slide, I want to talk about like so at the DOE level, what's happening is they have been looking into the AI and cybersecurity at the bigger scale. They're not just thinking about using AI for developing solutions that we have been doing for the past 10, 15 years. They're also trying to understand why AI need more better security. Because the AI, when it was developed, it's like you feed the model, model do something, and then model give you some output. But there are multiple ways AI could be compromised. So how to build the trustworthy AI models? That is one of our key research problem. And the third is the security from AI. So I think last few months I was attending this DHS conference and they were showing that you just go and ask the chat GPT that, hell, give me the network about the Texas power grid, how many PVs are deployed in which areas, what are the DRs located, what are the location of those DRs, as well as what is the risk assessment. The chat GPT can do all those things for you actually. So that's just an example that how that AI is also not like a good actor, it could also be a bad actor. And how you try to secure your grid from the bad actor, that's something we need to also understand. And one of our project is all about developing, like understanding how AI could be used in a bad ways and how they can be used to exploit and create like a payload or try to inject malicious packet, which was very uh, it's kind of happening, but AI could make things very faster and smarter. That even those attacker who are not that smart, they can understand how to use them, and they can try to create more attacks on the grid itself. So at NREL, we are trying to explore three different domains and see how we can improve ourselves in all three domain at this point. And then if you look into the capability that we had at NREL, we have been working on multiple domains. We have working on reinforcement learning. Had like a whole project on federated learning where we try to understand what kind of ways we can develop this idea to like manage the data set, make sure the data are not shared with multiple utilities, and how we can build different types of federated learning for the grid network. Then few colleague is working on generative AI and LLM, which is like an open secret. Everyone is using it. We are trying to understand how we can use it in such a way that it could be useful to understand the attack surfaces at the grid level. Explainable AI has been there too, where we try to understand that how the AI work itself. We don't want AI to be more like a black box, but more like a white box by understanding the features and how they are working to give you the right decision. Few folks at NREL are working on formal verification kind of approaches, and the reasoning behind is that they don't trust AI in general. They are talking about, like how the data center is going to consume so much power, and how do you validate that AI is doing well. So either one way is to stick to the formal verification like methods where you can verify if your AI inputs and outputs are doing well in the real-time testing. And then at NREL, we're also doing like red team testing on few seizure-funded projects where our goal is to try to understand if the solution has any vulnerabilities or what are the limitations of that kind of like work. So we also focus on red team testing, and the most important part is the CyberRange. NREL has invested a lot of money to build a platform which could scale the substation network, and I will also give you some insight about the CyberRange to itself. So going back to the CySAT tool, which I was talking earlier, it is kind of like based on this kind of life cycle model where it starts from the grid and then it collects the data set, it fuses the data sets into in such a way that it could be useful to detect anomalies. And then we try to, based on the given system, it give you like what are the ways you can mitigate them. And then once you do the mitigation, you go back to the grid. So it's like a closed loop cycle, very obvious, where you try to understand what's happening in the grid, then you try to take decisions based on the events that was detected in the grid network. And in that way, you are always monitoring your grid all the time and making sure there's no any cyber attacks that could happen in the grid network. And based on that, when we started the tool itself, we try to collect different types of data sets. That includes physical informations like grid measurements, network information that could be different types of network graphics, and then we have a log information that includes different types of device logs, syslog, and we combine them to help you understand what kind of events was there. So it could be any kind of cyber attack, it could be any kind of physical events like line maintenance problem or line outages. And then we also try to monitor them so that we see the normal healthy condition that could be also happening at the grid. So we call the CySAT is more like an advanced threat finder. That job is to understand what's going in the grid and then help the operator to take any action that might be required in real time. We try to add multiple features because that's not like a one-way problem, it's like a multiple lane problem. So what we do is we try to add multiple features and we are trying to also add more features. The basic feature was to try to visualize the grid. Like you want to see the grid with the cyber events, with the data, and that's why we added real-time visualization with all types of data sets. And then second was to build a better threat detection system using different types of ML capabilities. Third is the health assessment. So sometime even the attack is not happening, you want to monitor your grid health so that you can take any proactive decisions. And in when you have like a multiple dimensional data set and when you're running multiple dashboard at the same time with different functionality, you need something called event parser service. And its job is to parser the events or the logs or the data to the right functionality so that that functionality is working well. And also, any tool that we develop in the grid, we have to make sure that it could be scalable, could be deployed at multiple substations at the same time. And that's why we want to make the tool more virtual. And also, it could be run in containers so that you don't have to worry about any configuration. You just deploy them and it should be good to go. So all these features we have added and tested. But in general, I'm going to talk about the main key features, which is about the live data, AI-driven methods, also the grid health assessment. So the first one, which I want to talk about, is the live data monitoring. So this is the tool screenshots where you can see that the data are coming, and you can just configure what kind of data you want to acquire, and you can see them in more real time, which is very common in most of the tool that we have seen in the market. And you can see with the timestamp, and based on that, you know that whether your grid is working in a normal operation or there is some kind of transient happen because of cyber attack or maybe because of line maintenance. The second one is called health assessment metrics, where you can either assess the grid health at the device level or at the system level. And as you can see, we have put like a score matrix that is based on the deviation that's happening over the voltage or at the active power in the grid. So the whole system matrix is decided based on this score. If it is 100, that means it's in a good health. If it's less than 100 or is going down, that then you know there's something going wrong over there. And this health assessment is independent on what kind of event it happened. Any intrusion happen, any disturbance happen, this matrix could be useful out there. And it's based on the two different like a sub-matrix. One is called alpha, second is called beta, and we combine them to give you the final score. And the third is the machine learning based event detection or prevention. Here you can see that we have a data set that is coming from the sensor. We applied one called LSTM autoencoder to give you decision whether it's a binary or it's like an attack or normal for the binary classification. Once you detect anomalies, then you once you say it says true, then you go to the multi-classification of the event where we have deployed a method called transformer method, and that can tell you more details of what exactly event that happened or the attack that happened. So in that way, we are trying to have like a two-step process where we are not just detecting anomalies, but also trying to understand what kind of anomalies was there, which is very useful for the root cause analysis. Now here we can switch the LSTM with any other model. I'm just giving you one example that we're using LSTM, but that doesn't mean that it always has to be LSTM. We do like an offline analysis, and based on the performance of different models, we try to integrate them in real time. But this tool has that capability to integrate those models directly for real-time testing. One more thing I want to talk about is called network IDS, which is again very common. Like people who work in with the Snort, Geek, or Suricata, they know about this. What we are trying to do is that we are building some kind of a dashboard for better understanding of the logs itself. So here, say we have deployed Zeek, so you can see that what kind of signature was triggered, what was the source IP and destination IP. The source is like the it's like an IP where it was where the attacker tried to implement attack, and the destination is where the attack came from. So from here we can locate the IP of the attacker itself, and we can see what network or subnet has been compromised, and then use that kind of information to isolate that kind of subnet or the local LAN network. So having these kind of information is very useful, and we wanted to make sure that the operator doesn't have to have a detailed knowledge of the IDS itself, and it can use the same tool to understand what's going on within the grid network. So what we have done from the testing side, we try to see whether this tool work in real time or not. So what we have done is we have used the CyberRange to create this network with the control center environment, software environment. We have created all these virtual components, as you can see from the, so we have a control center with the SCADA system. We also added some database, and then we created like an internal attack within the control center that will try to manipulate the circuit breakers or mess with the grid. And then we other attack we did was with the another internal attacker within the substation network, and they will try to mess with your RTUs. So here you see these RTUs. They might try to DOS the RTU or try to do the ping scanning so that the attacker might know what information it's located inside the RTU. And the CySAT tool tried to detect the internal attacks happening within the substation as well as from the control centers. So we have tested these kind of like attacks using the CyberRange virtual network. In this case, we used the DNP3 to simulate the communication going between control center and substation. And we used the machine learning to detect anomalies that was coming from the internal attackers from the control center, and also try to give like a detailed classification of that attack. And any attack that came out from the internal within the substation, we use the IDSs, like intrusion detection system, to understand what kind of scanning they were doing for the grid. Here's a one quick example. So this is for the hydropower plant. In the hydropower plant, what we have seen is that there might be a hydro controller that might be connected within the same network. And we assume that our tool was deployed within the same network, and there was a maintenance laptop, and somebody messed with that maintenance laptop to give you more higher set point for the generation or the load. And when that happened, our tool was able to detect that kind of cyber attack. And for implementing this attack, we also followed the attacker attack MITRE framework so that we can make these attack more realistic. So we try to use the same attack vector that MITRE has given and implemented these attack, and see if our tool would be able to detect them or not. So that was one case study we did. And here's the simple like an example. So what happened in that case study was that when the tool was running within the hydropower network, you can see we can see the grid data coming to the tool, and it was very like normal with some minor oscillations. We used the modified 4-bus system, and then we had a maintenance laptop, and we tried to use that maintenance laptop to inject the load set point. So we increased the load set point. uh, as you can see over there in the screen, it says attack. So it was initially it was giving a nominal values, then we increased the load set point over there, and when that happened, you can see all these oscillations started coming up at the generation side as well as in the system. So when this kind of event happened, the operator doesn't, I mean, when you see the screen, you know something bad has happened, but you don't know where exactly that happened and how to detect this kind of events. So in this case, what we have done is we had the matrix. So matrix was telling the operator that there was something bad happened, and you can see the score has gone from 100 to maybe like 50. So that's like a very it's more like a red flag for the operator that something bad has happened. And then at the same time, the machine learning was able to detect this attack and also give you the detailed event classification. So as you can see, the transformer was able to tell you that there's a malicious attack happen. And this kind of like detection would help the operator to understand the nature of the attack and also try to use it to mitigate these kind of anomalies by either isolating that maintenance laptop or or trying to disconnect the cable. So this is how you can see the CySAT tool could be useful for the grid operators. We have also done case studies with the battery system. So this is for the battery system. In the battery system, what we have done is we assume there's a battery system with the controller and there was a switch. And again, we try to play with the attack. So here we try to mess with the breaker and the load. And we all, again did the same thing. We followed the MITRE attack framework and was able to detect these anomalies. What we have learned over here was that in case of battery, our accuracy was kind of less compared to the hydropower plant. And the reason is because the battery system has a lot more dynamics. They oscillate much faster because of low inertia compared to the hydropower system. So you might see that we might able to achieve like less F1 score is less than the hydropower system. And also there were like more false alarm that came up in case of battery. So these kind of analysis help us to understand how different system behaves very differently with the given same tool. And then we try to see what we can do to improve this, improve the accuracy or performance metric of the tool itself. The third work we did was something with the federated machine learning, and I know this is one of the hot topic which a lot of people are working into it. The benefit of having the FML approach is that you're not sharing data sets anymore, and there are different types of FML could be applied. It could be horizontal, vertical, distributed, and we have a lot of detailed work done in that domain also. And the whole idea is that you also try to implement the zero trust architecture, where you can also validate the parameter that is going from the substation to the control center. You are trying to develop a secure and privacy preserving approach where you are sharing the global local models outputs, local prediction to the global model without sharing any data set. And the second point is there's no any single point of failure. So say that if your local model get destroyed, still your global model could be useful uh, to develop a new local model. Same goes for your global model too, that once you have multiple models, you can still use those local model to develop a new model. So there's no any single point of failure in case of federated machine learning. And that's a huge advantage when you have a multiple substation as well as control centers working at the same time in real time at the grid level. And then you can also try to merge different types of models to create like a better models. And it works also with different types of data sets. So you had a battery, say you have one system, you had a battery, second you have a PV. You can still build a better model that can help you to detect all these different events happening in the different substation network. And then you can also think about if you can add like explainable AI into this, that could also help you to understand how this model is performing worse or better in a given condition. And one example I will tell you where we applied the FML approach is during the EV work. So what we have done is that the PGM regulation market, they allow EVs to participate into their ancillary services, and the users or the fleet operators also get benefit from that. And that is based on the FERC order. The FERC order tool that anyone any like EVs or hydropower, if they participate into ancillary services, they will get paid for the amount of service they have given. And as you can see that this is one of the report that has came out from the PGM that give you the detailed information about how the EVs has been tested and been used to support the regulation market. And more you supply like power for a longer time, more you will get more paid for that. And here what we have done is that we try to see what kind of cyber attack would happen when this kind of services are happening in real time. And I'll give you one example. Like say you have a 13 bus system and maybe one customer has this from this node had an EV that was injected with a local controller, and we have three EVs connected over there. And the PGM regulation market tried to send a signal called reg A. It could be reg A or reg D. The difference is that reg A is more like a slow, reg D is more dynamic. So say with the reg A signal, yeah, good.
그랬는데 교수님 때문에 주말에 열
So in this case, as you can see over there, that when these signals has been sent to the grid, they use like a DNP3 communication, and there are multiple ways attack could happen. So if you someone try to mess with these attack signals, then it's going to impact the grid itself. So how do you detect these kind of events in a such a way that you are not exposing the data set to the control center? So what we have done in this case is that we applied this architecture where we have trained the local model at the edge using the local data set, and then we try to federate them. We have used like in something called ensemble method, and here what we have done is that we send the local output predictions from these local model to the global model, and then global model take the average out of that and then help you to know what kind of anomalies was there, and then we try to notify the system operator. So we have integrated this whole framework within the CySAT tool and deploy these local models at the edge, and then try to test them to see if it works for the attack or not. And here are some of the performance measures. As you can see, we tried with multiple algorithms. What we have learned is that random forest and decision tree were very closely doing better performance compared to other approaches. And this is for the multis. That's why you see the accuracy is slightly less. In case of binary, it was giving more than 95, 96% accuracy. And then we also computed the area under the curve to understand like what are the false alarm which is coming. Mostly the false alarm came from some slower attack, like a ramp attack on the signal. The faster attack, like a pulse attack or a very high transient attacks, they were able to be captured nicely. Only those slow and dynamic attacks is where we feel like we need to do more training of these models so that it performance could be improved in further testing. So that was one of the results. I showed you that how AI could be used in multiple ways. I want to talk about the CyberRange. That is one of our platform, and DOE has invested a lot of money into this to build this kind of platform. And the whole idea is that we want to create something which is like for the automation and orchestration. So say you wanna implement virtual equipments with the hardware devices like RTUs. So we can integrate them directly into your experiment. So it's like a sandbox. That means that it will not impact what's going on outside the experiment itself. And you can integrate all different types of hardware components within the CyberRange platform. And then we also have like a smart meters that could be used to support AMI security problems. And then we use multiple different real-time simulators that has been deployed at the flattened campus, where you can try to play with real hardware equipments as well as energy storage devices. And then we also have a lot more PV installed there. There is a controllable grid interface that try to and its goal is to emulate the load profile. So say you have a data center load profile. You can use the CGI to emulate that load profile, and then you can test with solar or PV or wind to see whether these resources could support that much of power required by the data center. So we have this facility that could be useful in so many ways, and also we can also interconnect them with the cyber range to do like real-time operation or emulate any control center application. And there are a lot more things could be done here. And I want to give you example from this slide here. So this is what we have created in the cyber range. So you can see we have simulated distributed grid. We also have simulated the transmission level grid using the Helix platform. And then we also had multiple sites, one for the wind farm, as you can see over there. That could also be interconnected with in the hardware in the loop kind of ways. And then multiple substation devices could be interfaced remotely to support like a virtual relays, circuit breaker communication. And then we have multiple substation network going to the control center, and at control center, we can create multiple network. One could be your control center LAN A, where we can deploy different types of controllers. Then we also have an enterprise network. Here you can add all kind of IT-based services. And there's something called DMZ. DMZ is one of the ways you try to isolate the control center network and the IT network and only allow those files to be transferred, which is requested by the admin. And also they have like a like more like a server, so you can store the files the any application as a backup that that might be used to update your existing application going at the control center. So DMG plays a huge role, and it also makes sure that anything that happened at the enterprise do not impact your OT network or the control center network. So we try to simulate this whole different types of control centers, enterprise for transmission as well as distribution utilities. And also we integrated the whole architecture of the CyberRange with the AWS. So we try to understand what kind of application could be used within the AWS, and how we can do some kind of attack assessment based on the application that they have. And I will show you by a quick example. Like this is a cyber range, then we can connect with the AWS VPN, and then we can look into what application they have been running at the AWS and see if we can understand the impact if something goes wrong. Like for example, if someone tried to poison the data set, we learned that AWS has something called forecast. So if the data set get poisoned, the whole forecast accuracy was impacted. Um, so because of that. We don't have the solution yet, but we are trying to understand what are the ways we can compromise the AWS, either by the data sets or by sending the wrong model or the file. So we can understand that how much accuracy will get impacted if we somebody mess with the AWS or give you the wrong information during the cyber attacks and all. So we have tested this and we understand how to integrate the cloud with the cyber range and what impact it can create if something goes wrong in the experiment. Then it comes to explainable AI. So in the explainable AI, what we have done is that we try to understand why the explainable AI is useful though. And the first reason is the transparency. So the right now, like in the maybe in the 4 or 5 years before, what we were doing is that we try to use the AI model, do the testing, get the accuracy. Once we found the higher accuracy, we just move ahead. So and that's how we have been doing. We have been working with AI. It's more like a plug and play. Which one works better? Just use it and then write a paper or something out of that. But with expandable AI, you can have more understanding of how the AI itself work and how much you can trust your AI. Say like you had a trained AI model, but during the real-time testing, somebody messed with your model or try to poison your data set. Now your AI is not doing well in real time. So how do you do like a validation check whether your AI is working or not? So the explainable AI could be useful in that context. And also it gives you more trust that the output that AI is giving to you, can you use that output to make like a risk aware decision based on those outputs? And also like right now there's not much standard with the AI security itself, but I do believe that in future there might be a lot of more standard might come from the government to ensure that the like who'd be the responsible for bad AI decisions? Who's going to take that responsibility? So there are a lot of open questions right now that if AI do something bad, who should take the responsibility and who should be given the penalty for all the bad things that happen because of the bad AI? So it's not clear so far. Like I said, a lot of standards, we have a lot of standards, but there's not anyone that really focus on AI driven standard. There are some NIST standard that might have talked about it, but still it's not clear that when it comes to accountability of AI, who would be the responsible for the bad decisions. And what we have done with the expandable AI, I will show you with this quick demo. So what happened is that here we have added, so these input feature that you see over there, those were the part of the AI model to understand the decision, like is it a good or a bad? So let's see if I can play this. So what happened is that if you see it says no attack. That means there's no attack and you can see what features was useful when there was a no attack. And moment the attack happened on the bus voltage, you will see that what features were positively impacted or negatively impacted, that could also be seen here. So by using this kind of like understanding, you can get rid of those features which are not very useful in training your model or testing it. In that way, you can minimize your data consumption or computational power that is required to run these AI models. And this could be a huge thing once you start thinking about at the large scale. So in general, we can say that the expandable AI could be useful to understand how the features are working, what's the rationale behind getting the output, and also try to understand how these input features are useful or how they are contributing for a given event. And there are multiple models like SAP or LIME you can use it to make your existing model more detection uh, interpretable, and then also try to understand more in a more human readable ways so that you understand the alert and then use those understanding to take any decision. The last thing I would like to capture here would be the mitigation problem. So one of the ways we can mitigate the anomalies by deploying the deep reinforcement learning. And the way it work is, I will explain with a simple example. So you say you have a microgrid network, you have a local controllers and a secondary controller. The local controller job is to regulate the power sharing between multiple DRs, and they uses frequency and the voltage input to understand what set point has to be given. And then secondary controller try to give like a coordinated decision and help the local controller to try to minimize the set point gaps between local controllers and try to improve the grid instability in general. So there's a lot of maths behind this, but this is a benefit over there. So if you don't have a secondary controller, your frequency is not matching back to 60 hertz. But once you have secondary controller, you will see that your frequency is going back to the 60 hertz again. So there's a benefit of having secondary controller because secondary controller take care of the understanding of the local controllers and then try to give you better decision or a set point to improve your system frequency, or it could be also for the voltage too. And when we try to understand the attack, so say that somebody tried to mess with the measurements coming to the secondary controller, you can see how these different attacks could have an impact. The ramp attack could again impact your frequency. So does the step attack, and then pulse attack is more severe. And more you try to mess with using the pulse attack, you can see how the oscillations looks like, and that could have a cascading impact. So when for these attack in the earlier days, what we have done is that we try to look into a mitigation which is more based on taking the sliding average of the data set. So what I'm trying to say is that you what we do in the mitigation is when we know there's an attack, we don't use the attack signal but try to use the previous sliding window of the measurements as an average and then use that for the mitigation. And the main challenge in doing in that approach is there might be delay between the ideas sending you the alert and the way this mitigation model has been started. And I'll give you example to understand what I'm trying to say here. Say that there was a proper sine wave that was coming from the grid, from the measurement side. Now the attack happened at the 5 second, and you thought about, okay, when the attack happened at 5 second, how about we take the average like of the previous 20 sample? So in the ideal way, you will take the average from the time when the attack happened, that is up at the t equals to 5 second. But the IDS might give you some delay before operator even knows that there was an attack. So in that case, what happened would be that you're also capturing the bad measurements that has came from the attack because of the IDS delay. And as you can see, the impact over there that the green said here kind of help you to understand that we are capturing some bad measurements while doing this kind of mitigation. And and if you try to think from multiple ways this could impact, if the IDS delay is like a 10 second, then our mitigation will never work. And we call it like a static sliding average based mitigation. So in case of ramp attack, this was never able to recover your system frequency. Same goes for the higher IDS delay. If your IDS delay is say like a 20 second, you can see that it is even worse. So higher your IDS delay is, your static mitigation is not going to work. So this is a problem that we're trying to solve here. And now, what is the solution? The one solution would be to not use the static mitigation, but use like a reinforcement learning for cyber attack, where you had a something called the RL agent. They will try to get your input from the system. It could be the state input as well as the reward input. And based on these two input, they try to give you an action. So you have like a smart controller that is giving you a better decision based on the input and the state. And it could be used to give you mitigation during cybersecurity attack. And there are also multiple ways like these kind of controller could be useful in the power grid. And here is what we have done. In our case, we have taken input in terms of voltage, frequency, as well as IDS. And based on that, we try to minimize the deviation in the voltage and frequency. And then based on that reward computed, we try to send the action. And uh, and the whole job is to make sure your system has very small error at the voltage and the frequency level, and it should be it should work only when the IDS input is saying yes to the agent itself, because it's a mitigation. So mitigation has to work once you know there's an anomaly in the grid network. And this is how we have implemented this. So in this architecture, what we have done is that we implemented the RL agent at the system level, and it takes the input from the IDS. So whenever IDS says yes, the RL agent will get trigger and it will try to give an accent to the actuator over here. So we try to implement this boxes within the existing DR architecture so that it could be deployed in real time, and make sure that there are multiple local agents are deployed for each substation. So there's no any single point of failure. And then we have tested them for multiple case studies. And I'm giving you one simple example. Like I said, this was the static mitigation for say IDS for 20 seconds. Once we have deployed our proposed dynamic mitigation, you can see that how the use system frequency has improved from 60 hertz. There was a small deviation happen, there was some transient happen, but eventually it goes back to 20 hertz. So by having these kind of dynamic mitigation, you're trying to restore your system frequency close to what it was earlier. And we have a lot of maths behind this, but I'm just giving you like a context that by having this kind of dynamic mitigation is much better than having a static mitigation, which has not much information about the system itself. It just rely on the data set, which is not useful. By having the information about your system, your reward function, and the data set, you can build a better mitigation that can restore your system frequency in the real-time testing against different types of cyber attacks. And look like I have 12 minutes left, so I'm gonna show you one more slide, and then I'm open to any Q&A questions here.
Just to open up a Q&A in other 2 minutes, if you want to just spend the last slide here.
Yes. So in the future, what we are going to do is that we want to focus more into LLM-based ideas. We are trying to build the tool in such a way that it could be deployed in a sandbox environment, especially for the AI, and try to integrate more LLM-based features so that users can interact directly with the tool and they can get the answer they're looking for. Second thing is we wanted to do more testing because federated learning is one of the key ideas which is going across the DOE. They wanted to see more work happening in this domain, and not just for the power, also for the water. It could also be for the government network itself. So we're trying to develop more capabilities in this scope, and also try to integrate with the zero trust network. So those are some work we have been working around. We have some Caesar funded projects where we're trying to understand what are the ways we can develop more privacy preserving mechanism for the grid network. And the third part would be to focus more into the automated mitigations by developing more complicated deep learning methods and trying to integrate them with LLMs. So these are like a few words we are moving forward in general, and then we will always try to do the testing and then try to see how we can commercialize this tool with the different industry partners. So we are working around that part also. And with that, I will close my presentation, and I'm happy to take any questions at this point. So,
Thank you, Dr. Vivek, for your talk. Now people who have questions, either they can speak up or put their questions on the chat. Who wants to go first? Yeah.
Okay, so let me ask a question. Let me see, after listening at your presentation, I really want to ask a question. What is the size of your team? How many people?
So our team has around 60 to 70 people
Okay,
in the center. We actually our center was called Cybersecurity Center, and it has grown a lot actually in the past 2, 3 years. So yeah, my understanding is would be around 65 to 70 people within our group. So
I see. Okay, that makes sense because, the scale of the work is way too big. And so for the university, okay, actually, may not even be able to handle this scale, okay, of this workload. And I also see that, in your presentation, a lot of the underlying construction of the underlying supporting network, the framework, such as, the streaming of the event data, and in order to be able to feed into some underlying of the analytical framework. So for that thing, I want to ask, uh, how well that underlying framework had worked, in the sense that it will always get the data to be streamed without experiencing major interruptions.
I mean, like at NREL, we always have major interruption, Professor, actually, because um, what's happening is that we have been working in this domain, like I would say more around 9 to 10 years, and then we have a lot of people with the right skills, which take care of that. Like for example, I remember that, like like how you work in industry, like you try. So we have some researchers; they are very good at hardware in the loop testing. So they try to integrate the hardware in the loop thing, and then we try to capture the data. One of the key part is called event parser service, and I was trying to highlight that more because event parser service is not like a academic problem, but it's more like a practical problem. It's like how do you try to like collect a specific types of data set from the multi-dimensional database and then try to parse them inside the model or functionality that makes sense. So one of my colleague has like really good skill and he know how to write a Golang, like write the script in Golang, and his job is to parse the right data set inside the system. So I feel like even in this whole like cloud project, there are multiple challenges we have to deal with, and there's a whole team working on that, and they are very good at what they are doing it. And like Helix is always a big challenge to interface between transmission or distribution. So and we had a lot of projects. We had I would say we had around 40 to 50 projects. So what we do is that we have this kind of like system where once the project gets completed, we put them into the GitLab, then a new projects get started. We use the existing work that we have done and then try to figure out what new problem has came up. So by having a dedicated like a system and the platform, we are able to keep advancing ourselves in what we have done so far and how we can leverage that. And that is the best part of CyberRange is that it's virtual. So we always try to make sure that it could be automated as quick as we can. And we try to have a baseline model, baseline configuration that could be useful in any future work. So, and I feel like it's a lot, like it's like a dedicated team working the way you have seen in the industry. We follow the same pattern in in the lab too. We work as an industry, maintain the repo, find the right people with the right skill to do the job, and then we have to optimize our funding to make sure we align with our objectives. So there's multiple people doing multiple things, and then we try to eventually deliver what we were supposed to. So
Okay, thank you, thank you. So your team must have a lot of engineers. Must be. Okay.
yes, yeah,
Yeah.
yeah. I mean, we do have a the layoff happened, to be honest, in March because of all these changes. But before that, a lot of things were there. But now we are trying to optimize our like colleagues and the time and the funding, and hopefully maybe in next couple of years things might go back and we might be doing more work. So like the wind projects is almost gone. So all the work we have done on the wind is kind of not interested anymore to the DOE. Same goes for EV also. So I mean, like DOE does not want to see any EV work anymore. So you see how the changes are happening, and we are trying to update ourselves with the new changes happening in the at the government level. So yeah.
It's a temporary
Yeah, thanks
solution,
again.
temporary thing.
Yeah.
So we'll see that
Yeah.
things will change, But we have a couple of questions, I think when deploying a highly accurate reinforcement learning agent, what specific non-machine learning safety mechanisms or architectural components must be implemented to reliably handle the remaining rare, potentially catastrophic 0.01% failure rate?
Yeah, that's a tough question. You should ask this to industry, maybe who's deploying it. What I can say is that that the so here's the thing. One way I was working was to use DRL to do the mitigation, and then later on I worked on what are ways your DRL could be impacted by cybersecurity problems. So there are ways you can prevent those attacks, and the way is to you have to validate your model, your data sets. So always add like a zero factor mechanism when you are training your model, and then also make sure it is not getting poisoned. So the ways we can make sure our DL is working is by doing more online training. And I think it's a part of the DL itself. More you do like an online training, more the model will better. And the second part is to have a like a data set with lot more variance. So there's something called you need to maintain the bias and the variance in the data set so that your data is trained well for the DRL model, and then you try to test them for multiple scenarios that you had. When it comes to the real-time testing, if you do like a testing for a very different scenario, I'll be very careful because real-time testing there's no anything like going back. Once you do that, then there will be an impact on that part. So make sure your model is trained for the given data set. There's no any unknown data set coming up to the grid. That's why having a zero factor is always useful. Explainable AI is a big thing, like I said. Explainable AI can tell you why your model is behaving in this way. And there's also something called confidence factor. So if you have a higher confidence factor, then only your DRL should be allowed to take any decision or any control decision. If not, we should be also keep like a human in the loop there so that they can watch it and only they feel confidence they should use that to make any decisions. So
Okay, so we have one more question. Given that a standard random forest is an ensemble of non-parameterized decision trees and lacks the continuous weights used in traditional federated learning, what exactly is shared to support federation? And does federation actually add value or impact its performance?
yes, that's a very good question. So what you're asking is right. Random forest doesn't have any weight sharing mechanism. So what we do is that we try to share the local output of the model, and then we combine the local output in a weighted average fashion. So the way we did is that based on their performance during the validation, we give them a score. And then we use that score with the local output to compute a weighted average prediction for the model. So that's how the random forest work. But this is not the only solution. Now, it again depends on which architecture you had. Like I use them because my data set was very horizontal way. Like it was like a very like so the data that was coming from the area one was almost same as area 2 and area 3. So ensemble was one of the right ways to move forward. But say if you have a very diverse data sets, which is then you have to use something called vertical. And in case of vertical, you can either use split neural network. That is also very useful. And But again, if it kind of depend on the data set which method will is going to perform well. Like one of the studies what we have done, we have shown that the split neural network for the feature distributed machine learning performs better than ensemble one. But that doesn't mean that it would be always be true. So it's completely on a data set. In our case, we use ensemble. It might be that your students might come up with some better ideas to use vertical, and that also fine actually. So it's more like an offline analysis where you test all different types of mechanism and then you try to make a story out of that. Like, hey, I'm gonna go with this method because it has performed much better, and then use them for the real-time testing and integration. So
Okay. More questions? Any other questions from an Abhishek?
Yeah, actually, I have three questions for the expert. So I am currently new in this part of cybersecurity. So first of all, I wanted to know what is the current capacity of the RTU, which is there which is there in the means it is 16 bit. Previously, the RTU capability was around 16 to 32 bits. Now, has it increased or not? And also about the latency, what happens when we are applying these neural networks, and these are, since these are online neural network trained, so there would be some latency in the particular operation. So can
yes,
you give some light on that? How means your algorithm are handling these two things?
yes. So Abhishek, we had a paper on that part where we talk about the latency, and I'm trying to memorize them. The latency was like coming in terms of like uh, less than second, because these models work very fastly. So if I remember, the latency that we have computed was always less than a second. And the controller that we have considered, like for example, this controller, you see the regulation market, that happen every 2 seconds. So it should not impact what machine learning is doing within less than 1 second. Same goes for microgrid also, like for the deep reinforcement learning. So we always try to make sure that the latency that is coming should always be less than latency for wide area controller or any controller. Otherwise, it will make no sense to
Yeah,
integrate machine learning for a given controller. If they are super fast controller, then you have to again find the right machine learning to do that so that you're and yes, and but again that's also more complicated question because latency which I'm talking about is only for the model. There would be more latency that might come when there's a communication happens. So it's really useful to do like complete assessment of not just looking into the model latency, also the communication latency or the sensor latency, which is always hard to know because unless you deploy them in the field, you will never know how the latency looks like eventually.
yeah,
So yeah, so if we do like any field deployment, then yes, then I will tell you the right number for that latency. But from the AI side, I never see any problem in terms of latency because it's always a small fraction actually. And asking to your second question about the RTUs, so the RTU that we had at NREL is not like we are building something. We mostly acquire from SEL or Eaton. So
okay,
whatever the RTU they had, we just acquire them, or we use like an RTAG. So RTAG is like an RTU, but also it you can add control logic to make it like a local controller. So what you saying is maybe right. The 16 or 32 bit is what they had, if that's what's showing on their web page. But we are not doing anything like improvement in their RTU performance and all. If we
hmm,
find a better RTU with higher performance, we will just buy them, and then use it for
yeah.
the project. So
I was asking because when there are a large number of data samples to be processed, for that
yes,
only specifically, why do we require this high bit processing? And
Yeah.
one more thing regarding that data which you have shown in one of the slides with timestamp and all, no? Is that data available for the public use for research?
Which
The
data?
grid data. In the some of the starting slides I have seen.
Okay, let me see. Oh, you mean these data?
Yeah, this data set, the upper one.
Yeah, the data sharing is something I need to check because right now it's kind of hard to share anything because of all
Uh,
the changes happening. But yeah, we have not said anything outside because it might require approval from Caesar.
That's what I was thinking. If it is open, because I am also doing research in this portion only. So
Okay.
if some practical data set is there, then it would be very much good for validation purpose and all.
Yeah, I would say maybe reach out to me, and I would see what data we can share with you. I mean, or in the future, eventually my plan is to make it more open source so that more universities can use them. But it's gonna take a while. Things are really slow in the at the government like the national level compared to other academia actually. So it always
Yeah.
takes more like than I expect. So yeah, I mean, hopefully by next year we can try to make this data open source. So yes.
Okay, any other questions?
Okay, thank you very much.
Anybody else has any other questions? We are running out of time. Nirup, you have any last question?
Yeah, and one more question for Dr. Singh without taking up too much of his time. Firstly, thank you for your presentation, Dr. Singh. So you said there are multiple data sources like grid info, network info, log info. Which of these data sources are more important than others? Is that the right question to ask? If you have computational constraints, if there are outages, which of these are more important?
Yes, this is the right question. I feel like because eventually we cannot store all the data sets, so we have to do something to find out the right data to store, or it also impact the computational power of the any server. So mostly the grid information is the right information to store, where I've seen that if you can store the power system features measurements data set, you can mostly get most of the information that you're looking for. But at the same time, there are logs like IDS logs, because IDS are really good. So sometimes their output is very useful in developing a better machine learning models. So I would also keep them as the second priority list. And then in terms of network traffic, most of them are like a garbage. But then if you can do some more features computation from the network traffic, like you can analyze the bandwidth, or try to understand what the size of the payload, and if you can use them, then you can also try to detect some cyber attacks, which is more like an IT nature, like DOS attack. So that's where the network information is very useful because you can see those IP risk coming from the random sources than the legit network. So it kind of depends, but like I said, grid information is very useful because any attacker is first thing is to impact the grid, and when the grid gets impacted, the grid information is where most of the impact could be seen. So I would give high preference to the grid information. So
Thank you, Dr. Singh. Yeah, thank you, Professor.
Uh, like we're all run out of time. So thank you, Vivek, for doing this presentation for us. You will receive a nice plaque from UND for your time and look forward to working with you on different proposals. Appreciate again for your continuous support to the center.
awesome. Thanks everyone, and looking forward to maybe meet you again next time. So yeah.
Thank you.